Hello and welcome. Here's a comforting thought. When things go wrong, what can you always count on? Your fingers. And if that wasn't comforting, well, you can take comfort in the fact that we're going to learn something amazing today, the fundamental theorem of calculus. Let's get started. You might recall from packet 22 that we were learning how to visualize an estimation of the distance traveled using velocity samples at 5-second intervals. So the picture to the left is showing that. Remember that along the x-axis we put time, t, and here are 5-second intervals. T equals 0 to t equals 5 is the first 5-second interval, and then t equals 5 to t equals 10 is the next 5-second interval, and so on. And at each of these times, at 5-second intervals, we would take a sample velocity reading. So at t equals 0, we have a velocity of 25 feet per second. And then at t equals 5, we have a velocity of maybe like 37 or 38 feet per second. I can't remember what it is off the top of my head. Now there's actually velocity values in between those time values. We just took sample readings. So there's some kind of smooth, continuous velocity function that's going through these sample velocity readings, going through these points. But all we have to work with are those sample velocity readings. So what we did is we said, let's suppose, if we're trying to find distance traveled, let's suppose that the velocity on the first 5-second interval is 25 feet per second. So we had our initial velocity reading of 25 feet per second. Let's suppose that for the first 5 seconds, that's how fast we're traveling. Knowing full well that the velocity is changing, but this is our best estimation at this point. Well, then at t equals 5, we have the let's say 38 feet per second, and we would use that as our sample velocity for the next 5-second interval, and so on. And it turned out that when we were trying to figure out what distance was traveled on each of those 5-second time intervals, let's just focus on the first one. Well, we took the 25 feet per second and we multiplied by 5 seconds. And we said that that was the estimated distance traveled. So the seconds cancel, you get 125 feet. But that corresponded, visually speaking, with the area of that rectangle. So this is the area of the rectangle. And we mentioned that the units look a little bit funny because you get 125 feet, and normally you're thinking, isn't area square feet? But here the sides of our rectangle were not exactly distances. One of the sides was measured in feet per second, and one of them was measured in seconds. So we end up getting units of feet. But if you just take the numbers themselves, the 25 and the 5, and you multiply them together, that's like doing an area of a rectangle calculation, an area of that rectangle. So writing what this 125 feet was, it's the estimated distance traveled in the first 5-second interval. Now, if you think about distance traveled, you can think about that as being a change in position. It's going to be your final position minus your starting position. So another way to write this would be, if you had a position function s of t, you could write that s of 5 minus s of 0 is approximately equal to 125. Right? The ending position at t equals 5 minus the starting position at t equals 0 would give you the total distance traveled, 125 feet. At least that's the estimated distance traveled. But let's see if we can make our estimation better. What if instead of taking sample velocity readings every 5 seconds, we took sample velocity readings every second? Now we're going to get more accurate velocity readings in between all of the previous intervals, right? From 0 to 5, we're going to have now 5 readings instead of 1. So the diagram on the left, or the picture on the left, the right, is showing that. So it's taking that first 5-second subinterval, breaking it up into 1 second subintervals, and so for each of these, we're going to get a velocity reading. That's what these extra dots are here on that first 5-second interval. Excuse me. And what we can do is use, for example, at t equals 0, the 25 feet per second. Now we're using that as the sample velocity for only the first second. Because at t equals 1 second, we have another sample velocity reading. So that's going to be whatever that is, like 28-ish. And we'll use 28 feet per second for the next 1 second interval, and so on. So we're going to get 5 calculations just on that first 5-second interval. And again, each one of those calculations will correspond with the area of the rectangle in the picture. So here we have 5 rectangles to add up for the first 5 seconds. And if we add up the areas of each of those rectangles, which again is computing the distance, the estimated distance traveled, then that'll give us an estimated distance traveled on the first 5 seconds. So the area would be 25 feet per second times 1 second. All right, second out. And then, so that's just the first rectangle. And then the second rectangle will have a calculation, and the third and the fourth, and then the fifth one, that looks like it's about 35 feet per second. So last one, let's say it's 35 feet per second times 1 second. So that last, from t equals 4 to t equals 5, our estimated distance traveled is 35 feet per second times 1 second, which is 35 feet. Excuse me. And so this is going to be 151 feet, approximately. This is a better estimation. We could even write it's a better estimation of the actual change in position. It's a better estimated of the distance traveled on that first 5-second interval, which we can represent as the ending position minus the starting position. Now, we can keep making this process even better. We could take sample velocities every half second, every millisecond, every nanosecond, closer and closer to every instant in time. If we could sample at every single instant of time, then the picture would look something like this. Those rectangles would more and more tightly fit the area underneath that velocity curve, until what you're looking at is basically the area under the velocity curve from t equals 0 to t equals 5. So the picture that we would look at for this area is showing us the exact distance traveled in the first 5 seconds, or the first 5-second interval. Right, because the more sample velocities you use, the better your approximation is. So if we use an infinite number of them, so sampling at every single number between 0 and 5, which there are an infinite number of numbers, you can convince yourself of that because you can always take 2 numbers and divide by 2 and find one in between, as an example. But there are an infinite number of numbers between 0 and 5, and so there are an infinite number of possible velocity readings you could have. And so all of those, if you put them together, you would get this exact area under the curve, which is the exact distance traveled in the first 5-second interval. So the key thing here is that the area under this curve is representing the distance traveled. So the area under this velocity curve is representing the distance traveled on that interval. But the area under the curve, we have a notation for that now. This is the integral from 0 to 5 of the curve, the velocity curve. That's the definite integral that represents the area under the curve. Right? We could use this to calculate the area under the curve. But the great thing is here, we have this other interpretation of what the area under the curve, how the area under the curve can be calculated. It's the change in position, right? We said this is equal to s of 5 minus s of 0. It's the change in the position. So on the one hand, we have the area under the velocity curve from t equals 0 to t equals 5 gives you the distance traveled in the first 5 seconds. Whereas on the other hand, you could take the position function at t equals 5 minus the position function at t equals 0, and that's another way of calculating the distance traveled on that first 5 seconds, second interval. So these two things are equal to each other. And this is what will give you a really good intuitive understanding of where the antiderivative now comes into play. Notice that the integral right here, the integral of this velocity function, is equal to something involving the antiderivative, right? The antiderivative of velocity is position. So if we wanted to think about this, if we have the velocity function and we take an antiderivative, we get the position function. Just like if you take the derivative of the position function, you get velocity. So if you go from the velocity function to its antiderivative, which is the position function, now you've transformed this integral into just another function subtracted, like with two function values that are subtracted. It's a much easier way of doing this calculation than going through all of the pains of writing this as the limit of an infinite sum, or the limit of a sum. So the key here is to notice that the position function is an antiderivative of the velocity function. We showed it visually here, and this is one of the ways we kind of saw how to understand the relationship between position and velocity. So going from position to velocity, it's derivative. Going from velocity up to position, it's antiderivative. Here's another way of writing that. The derivative of the position function is velocity, and therefore the position function is an antiderivative of velocity. Just different ways of writing the same thing. Now I think position and velocity can really help to ground your understanding. If you think through this example, these pictures, and through this example again, it can really serve as an anchor to understanding this first fundamental theorem of calculus, this first part that we're going to look at, which is actually the quote second part. So let's write though in general, this works for velocity and position functions, but it could work in general for any function really. There was nothing special about the velocity and position functions. That was just our example for intuitive understanding. So we can say that in general, the integral from a to b, your start of your interval to the end of your interval, of f of x dx is big F of b minus big F of a, where here big F is an antiderivative of little f. Remember the way we defined it, if you take the derivative of big F and you get little f, then big F is an antiderivative of little f. This is kind of like your checking process right here, but it also shows that big F is an antiderivative of little f. So the picture here would be, here's little f, here's big F up above. It's an antiderivative of little f. There we go. So what we can do is say, so the area under the curve f of x is related to the antiderivative in this way. Another thing to note is that if you rewrite this just a little bit, so instead of writing little f, if you write big F prime, right? Those two are equal, little f and big F prime. Let's write it here. We'll write it in a second here. We're going to write what it does. You're going to be able to see that it undoes the integral is undoing the derivative. So let's write it using big F prime of x. Oops. So notice here, take big F, just look at big F here, take its derivative, and then apply the integral, and the integral will undo, in a sense, what the derivative just did, getting you back to the original function, the big F that you started with. So if you do take big F, take its derivative, then do a definite integral, then you get back to big F, or at least you get back to using big F in this expression here. So in a way, it's undoing the derivative. Okay, so this statement that we made here, the integral from a to b of little f of x dx is equal to big F of b minus big F of a, so antiderivative at b minus the antiderivative at a. This is what we're going to call the fundamental theorem of calculus part 2, also called the evaluation theorem. So that's the next part, next page. Now f has to be continuous for it to be integrable, continuous on the closed interval from a to b. And big F can be any antiderivative, it turns out, of little f, and this is still going to be true. So it doesn't have to be a specific antiderivative, just any antiderivative. Now often we're going to just choose an antiderivative that has our constant 0. That way we don't have to constantly write a constant. Didn't mean to say it that way, but we don't have to be always writing a constant. So we'll just conveniently choose the antiderivative that has a plus c of 0. So in example 1, it says evaluate the integral from 0 to pi of cosine x dx. So then we can think off to the side, well, what's an antiderivative of cosine x? This is like our little f, I should mention. Cosine x is like your little f. If you want to talk about your a and your b, here's your a, here's your b. A is 0, b is pi. So what's an antiderivative of cosine x? If you said sine x, then that would be correct. Technically, the most general antiderivative is sine x plus c. But again, we're just going to choose our c to be 0 so we don't have to write the plus c. We just want any antiderivative, not necessarily all antiderivatives or a specific antiderivative. All right, so now it says that what we can do is write big F of b minus big F of a. So that would be sine of pi minus sine of 0. Let me try to match this up here. This is big F of b minus big F of a. All right. Now sine of pi is 0, sine of 0 is 0, so we end up getting 0. That kind of makes sense, right? If you take the graph of cosine, I'll draw all of cosine. Well, not all of it, but one period of cosine. Kind of makes sense because here, if we're trying to find the integral from 0 to pi, well, the first part of that area is from 0 to pi over 2 is above the x-axis. The second part of that area is below the x-axis, and they take up the same area, just one's positive and one's negative. So they perfectly cancel each other out by the symmetry of cosine. So that's why we're going to get a 0 here for the answer. The net area between cosine x and the x-axis from 0 to pi is 0. Great, so that checks out. Now, we're going to want some handy notation. A lot of times when we find an antiderivative, we're going to want to simplify inside of the antiderivative first before we start plugging in the b and the a. But actually, let's just take a moment to celebrate. That took way less work than trying to take the interval, find our delta x, find the x sub i's, plug x sub i's into cosine, try to figure out how we would even write those summations and into a closed formula, and then at the end take the limit as n approaches infinity. Doing the skills that we learned in packet 23 for this integral would just be a real nightmare. But now that we know about the fundamental theorem of calculus part 2, we can do it easily. We just find the antiderivative, or an antiderivative, of cosine x, and then plug in a couple of numbers and subtract, and that's it. That is an amazing accomplishment there. We now can do these problems much, much easier than in the past. So this is a really amazing connection that the area under the curve is related to the antiderivative. Okay, so we said we want some notation. Enough getting excited. So here's the notation. If you find your antiderivative, like we had sine x here, but you haven't plugged in the limits of integration yet, so haven't plugged in the b and the a, then what you could do is just write this little notation, this temporary intermediate notation, to help you keep going without having to do stuff off to the side. And also allows you to simplify your antiderivative before you plug in the limits of integration. Now, if your limits of integration have more than one term, then oftentimes you would put like brackets around both the beginning and the end, and then you would write the a and the b down here and up here. If you only have one term, a lot of times you'll see it without a bracket. So this is like if one term. Then you don't need to put that left bracket because it's kind of understood where you're plugging it into. And then what both of these mean, though, is big F of b minus big F of a. They mean the right-hand side of the fundamental theorem of calculus. So just a step along that direction. Let's look at example 2 to see how this works. So here, we're looking at the integral from negative pi over 2 to 0 of secant x tangent x. So then we're thinking, what's an antiderivative of secant x tangent x? If you said secant x, that would be correct. That's only a single term, so I'm going to put a bracket right here and put negative pi over 4 to 0. And then what this means is plug in the 0, put a minus, plug in the negative pi over 4. Secant 0, put a minus, secant negative pi over 4. And secant 0 will be 1. Secant negative pi over 4 will be square root of 2. So we have 1 minus square root of 2. Okay, so pretty straightforward. Now, the next example, we have a little bit more complicated function inside. We have 2 over 3 times square root of x minus 4 over x squared. We'll want to rewrite these as x to a power of something before we try to find an antiderivative. Let's do that first. So we'll write the square root of x as x to the half. We'll write 4 over x squared as 4x to the negative 2. And don't forget your dx. Always that integral sandwich, right? The integral goes with the dx. Okay, so now what we'll do is the constant coefficients will hang out in front. We're going to add 1 to the exponent, which gives us 3 halves, and then divide by 3 halves, which is like multiplying by 2/3. Dividing by a fraction is like multiplying by the reciprocal. And remember that our little trick here for adding 1 to a fractional exponent is just add the denominator to the top to give you 3. So 1 plus 2 gives you 3. And then the denominator stays the same. The reason that works is because you can rewrite 1 as the denominator of the denominator. And so you're basically just adding the denominator to the top. So then here we have the negative 4 still here. We've got add 1 to the exponent gives you negative 1. Dividing by negative 1 is like multiplying by negative 1. So we end up with something like that. And then we put our limits of integration, 1 and 4 here, to remind us what we're going to be plugging in. But before we get there, let's take a moment to simplify. Always good to simplify. We have x to the 3 halves plus 4 over x from 1 to 4. That's how you can read that. Now we can plug in the limits of integration. First we plug in 4 into the whole thing. 4 to the 3 halves plus 4 over 4. then we're going to put a minus, and then we're going to plug 1 into that whole thing. So we're subtracting the whole result of plugging 1 into this. So we have to open up some parentheses here because we have more than one term. Here we have 1 to the 3 halves plus 4 over 1. Now, 4 to the 3 halves, here we can take the square root of 4 to give you 2, and then cube it to give you 8, plus 1, and then minus 1 plus 4. So this will give you 9 minus 5, which is 4. Okay. So again, this would represent the area under this curve, whatever it looks like, from x equals 1 to x equals 4. That area would be 4. So that's pretty amazing. We're able to find areas under any function that we can find an antiderivative of. Okay, so last one here for this video. We're going to find the integral from -3 to -2 of dx over x plus 1. Just a reminder that if you see the dx on the top, that means 1 over x plus 1 dx. You can always put the dx off to the side, just as a reminder about that. And so we'll want to find an antiderivative for 1 over x plus 1. Now you could use a u substitution here, but this one can be done mentally. We can think, all right, this is going to be something like ln absolute value of x plus 1. We do have to worry if we take the derivative, do we have any constants to worry about here? And turns out not, because the derivative of ln absolute value of x plus 1 will be 1 over x plus 1 times the derivative of the inside, but that's 1. So no extra constant to worry about here. Now that's just a single term, so I'm going to get away with a single bracket. Now we're going to plug in the upper limit of integration and then the lower limit of integration. Oops. Said I would plug it in, but I didn't. So this is ln, let's see, -2 plus 1 is -1. Ooh, but we have those absolute value bars to make it positive. Good thing we put those absolute value bars there. And this is one of the points of this example, is make sure you put those absolute value bars there, because now we can handle the such an integral, right? When you have 1 over x plus 1, this can accept these negative values, -2, -3. You can plug those into 1 over x plus 1. So there should be some area under the curve here to be spoken of. Now if you didn't include the absolute value bars in the ln, you wouldn't be able to plug in -2 and -3. Those would give you a negative inside the ln, and that would be undefined. So but because we have these absolute value bars, we can take it. Our domain has not changed as we took our integral, or our antiderivative, from 1 over x plus 1 to ln absolute value of x plus 1, whereas it would have changed if we hadn't had the absolute value bars. Okay, so good thing we have those absolute value bars. Now, here we've got -3 plus 1, absolute value of that is 2, and ln1 is 0, so we end up just getting -ln2. Okay. Thanks so much for watching this video, and see you in the next one.